Hello and welcome back to another episode of Math with Sohn. Today we're going to be doing a linearization question, and a very popular one at that for AP Physics 2. But if you're just practicing linearization, this is a good practice as well. You do need to know this formula. Whenever you have light coming into any sort of surface that it can go through, not a wall, it will bend and it will refract in that light, okay? And depending on the surface, it will either bend away or bend towards the normal line, which is this dotted line right here. And the formula for that is N1 sine theta is equal to N2 sine theta. Technically, this is incident, refraction, or going in, going out. Okay, so N1 I'm going to call incident, and N2 I'm going to call refraction, which a 2 can be turned into an R really easily. Okay, so that is the formula. And here we have recorded a whole bunch of things. And we even did we did sine of that angle, which was very nice of them. All right. They tell us the wavelength. 632 nanometers is the light wavelength. I do not believe that matters. What are we asked to do? We want to determine the index of refraction of plastic. And did it come from air? I need to read that. The students are given that. Semicircular. The aims, the red layers with that. At the center of the black side, the ray is reflected from air. Found it. From air. If it's from air, the index of refraction of air, if you're in AP Physics 2, is common knowledge. If you're not, but air's index of refraction is just 1. So 1 sine theta incident is equal to N2, or refraction, sine theta refraction. If we want to find sine theta refraction, we are going to make this the y value and this the x value, and that makes NR the m. No big deal. So that means that these are going to be the y values and these are going to be the x values, and we don't have to do anything else. All right. On the graph, draw a line of best fit, determine the slope to determine the index of refraction, and it's nothing crazy. That is the index of refraction, is the slope. So let's plot the graph. We have incident 0 and refraction 0. Incident is 0.26, so we need to go from 0 to 1 and from 0 to 0.7. And oh my gosh, this graph is blurry. If we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here, I'm going to count by 0.1s for the y because the y values need to go up to 1. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. And then I might as well count by 0.1s as well for the x values because that would get us to around here. That seems like more than half. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. And we would need to label this sine theta refraction. And we would need to label this sine theta incident. And sine theta is doesn't have a unit. To my knowledge, sine of an angle is just a length. So I don't think this has a unit. I could be wrong. I hope I'm not wrong. Because I'm not putting a unit down. Okay? So we did that. Now we just have to plot the points. So we have, I'm going to plot those real quick. Incident and refraction. Refraction's that. We got 0, 0. Let's make sure we plot it because you never know when you're going to need that point. We have 0.26 for y and 0.17 for x. 0.17, 0.26. Looks right there. I'm going to do this in pink because this, well, black's showing up a little bit, but I'm going to do it in pink so you guys can see it a little bit better. Then the next point is 0.36 for x and 0.5 for y. 0.36, 0.5, 0.36, 0.5. This is about as blurry as it gets. The next one is 0.5 and 0.7. 0.5, 0.7. It's technically 0.71, so I'll go up a smidge. 0.6 and 0.87. 0.6. 0.87 is right about there. And then 0.7 and 0.97 is close to 1, but not quite at 1. Now here's the trick. You draw the line of best fit. You use a straight edge if you got one. You use a calculator if you don't. Which didn't work out for me last time I did this, but I'm going to try it again. You go, whoosh. Mine's a little too high, so I would lose points. So try and be better, or use pencil. Like it should be more like that. You cannot pick points that are on your data. You cannot pick points that are on your data. So even though these were great in the fact that they were using 0.5 and 0.7 and all that stuff, you can't use it. Okay? You can't pick points that are on your data. So if you can't pick points that are on your data, either A, extend your line, which is what I'm going to do. And I'm going to, well, it doesn't make it to 0.8. I'm going to pick 0.1 and 1.5. So this is going to be 0.1 comma 0.15. 0.1 comma, oh my gosh, 0.1 comma 1 point, fifth time's the charm, 0.15. 0.1 comma 1.5, 0.15. That's my first value right here. And then I have to be careful not to pick a value that is my data point. I've used 0.7. I don't get to 0.8 according to my graph. 0.6 was also used. 0.5 was used, so I'm going to use 0.4 perhaps, which looks like it is just below the 0.6. So it's 0.4 comma 0.58. Okay, you cannot use your data points, and it should be points that are further away than that. That makes it work better. I didn't want to find one that went through perfectly. I probably could have found one. Well, let's do the slope formula. Let's do it. We got 0.58 minus 0.15 over 0.4 minus 0.1. Do the math. 0.58 minus 0.15 divided by 0.3, and you get a slope of 1.43 repeat. Ask yourself, what does the slope mean? In this case, it only meant the index of refraction. Okay? So, the slope is 1.43 repeat. The n of refraction is also 1.43 repeat, or you could just say 1.43. Okay? That is all for this video. If you only wanted to learn about the idea of linearization. If you're in AP2 and you want to learn a little bit more, they want to confirm the results obtained in Part B by using the critical angle for the plastic. Describe an experimental method that the students can use to measure the critical angle. Indicate how the index of refraction can be determined from this measurement. So the critical angle would be when everything gets reflected. Okay, so that means that, let's say we're going in here, okay, and notice how it's going in here, and then it gets closer and closer to this line. See how like this is a bigger angle than that? And it makes sense. The incident angle is always bigger than the refraction angle. In order to determine the critical angle, the angle in which no refraction occurs, I'm pretty sure you got to go the other way around. Okay? So let's see. If we go the other way around, it would eventually, so what would happen is, imagine we take the semicircle. Let me draw it over here. Imagine if we take the semicircle, if we went this way in, we got our normal angle there, it would end up going and bouncing that away. It would be bigger, right? So that incident would now be the refraction angle, would be bigger than the, which was the refraction would be now the incident. So internal refraction, total internal refraction, which is called the critical angle, is whenever going in ends up making it to where their angle here is just simply too big, and it'll eventually turn into a scenario where if we draw our half circle here, you draw it, if this angle's too big here, instead of it going through, it'll all just bounce out. And that's what happens when the angle leaving is equal to 90. That is the ultimate point when, if that angle equals 90, that angle doesn't exist anymore. It is all being, instead of refracting, reflected, and that is called total internal reflection. So you would need to put the laser from the plastic and shine, gradually increase the angle until the laser leaving and going into the air stops, goes away, and all of the light is reflected. Now, does it say to design an experiment? It wants to confirm, use the critical angle, describe one experimental method. Did we say that? Laser and plastic shine, gradually increase the angle, that is the angle incident inside the plastic until that goes away. Indicate how the index of refraction could be determined from this measurement. Okay, so now we would have to think here. It'd be n refraction, which is now incident. Sine theta incident would equal n of air, which is 1, sine of 90. Okay, so we would be able to do n refraction, sine theta incident would equal 1. What is sine of 90? Sine of 90 is, I don't remember. Sine of 90 is either 1 or 0. It is 1. So if your sine theta incident, whenever you're going in, whenever it all gets reflected, is equal to 1 over the index of refraction, which barely fit on my paper, then you would be able to confirm it, and you would have to write more words. But I'm out of room, and I'm out of time. I will see everybody later. Until next time, stay positive. Bye.